Okay, in this video, I use a concrete example to illustrate the two inequalities we've found above. One is that the error, maybe let me start this way. If we estimate an infinite sum by a finite number of sum, then the error, which is denoted as Rn, the error we commit in this estimation is less or equal to integral from n to infinity f of x dx, where f of n is equal to what? No, not f of n. F of k is equal to what? Ak. Okay, so just replace k with x, and then that's your ak is your fk. Okay, we've also seen that not just that we can estimate the error we are committing, but we can trap the exact estimate in between these numbers. We can trap the exact estimate, okay, in between these numbers, which is very nice in even getting a better estimate. Okay, so these are the two things we've seen, and I think example will just make this clear and concrete. So let's start with first example. This is problem 36 in section 11.3 of Stewart's text. So say the first one, A part, says find the partial sum Sn of the series. So let's start with A. Find the partial sum Sn of the series. So we know that Sn is nothing but what? Here n is 10, sum from 1 to 10. The series is 1 over, so just replace n with k, it doesn't matter, k to the 4. So this is exactly what? 1 over 1 to the 4 plus 1 over 2 to the 4 plus 1 over 3 to the 4 plus dot 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 up until what? 1 over 10 to the 4. And if you plug this into any graphing calculator, I think you get this. You get 1.082036583. I use approximation sign because calculator gives us the approximate value, right? Okay, that's the first part. And then it says estimate the error in using Sn as an approximation to the sum of the series. So it's simply asking us to find a bound for Rn. So this is less or equal to, in general, is to infinity of 1 over x to the 4 dx. So if you integrate this, this is actually negative 1 over 3x to the third, then evaluated from n to infinity. So clearly when you plug in the infinity or take limit as t or whatever goes to infinity, then this is 0. So what will be left is negative this, which will be positive 1 3 to the third. So using any n to estimate this series, this is the error you commit. Now in particular, when n is 10, the error is less or equal to 1 over 3 into 10 to the third. Then work this out. This is exactly 0.000333333. Just make it same decimal place as this one. 9. 1, 2, 3, 4. Okay, so this can be shortened as 0.003 with a bar, showing that it repeats. Okay, so if we approximate this infinite sum with a finite sum, the first 10 terms, then this is the error we are committing. Okay, that's the first part of the problem. So part B, maybe let me drag this down. Part B says use 3 with n equals 10 to give an improved estimate of the sum. So 3 is actually what? This bound that traps the actual sum between two numbers. So let's use that. So B, let me just make good use of this. So let's start here. B, so we have S10, use brighter color. So we have S10, integral from 11 to infinity, 1 over x to the 4 dx is less or equal to the actual sum, which I will denote as S, and this is less or equal to S10 plus integral from 11, it should start from 10 to infinity, 1 over x to the 4 dx. Okay, we've computed this one. So let me just copy this. I've computed this. So I copy it, then I paste. We've computed this to be this. And this one we see it's nothing but what? The same integral here. So we just replace n with 11. So this is 11 to the third. Then this is less or equal to the actual sum, and then it's less than this one again. So let me paste and remove this. Then plus, again, this integral is 1 over 3 10 to the third. Okay, so if you work everything out, you get that S lies between 1.082287 021. The actual sum lies between this 1.082369916. And this is very nice because we have freedom to choose where this S belongs. Now we can even improve this by taking average of these two or doing something else. Okay, so the B part actually says we should give an improved estimate of the sum. So an improved estimate, so an average of the bounds is an improved estimate of the true sum. So let's take average. So let's just denote it with S bar. So this will be 1 plus, maybe I can even copy this and paste. Copy and paste. So I have this, then plus copy again, paste, oops, paste, okay, and then we divide by 2, and this turns out to be 1.082 328469. Okay, we do not know exactly how better this is compared to the actual approximation we have here until we try to compare them with the true sum of this series, okay? And that's exactly what the C part says: compare your estimate in part B with the exact value given in exercise 35. So it turns out that it turns out that Euler, probably using some advanced mathematics, was able to find, or tricks, was able to find that this series is actually what? Exactly pi to the 4 over 90. And this is given in what? Exercise 35 of section 11.3. Just exercise before 36. This one we're working on. So, if you work this out using calculator, you get an approximation. It's approximately 1.082323234. So let's see how good we have done using the average of the bounds and also the first 10 terms. Okay. So error in the actual error. So maybe let me say the actual error. When you use the first 10 terms is going to be, let's say, pi the 4th over 90 minus S10. Just put absolute value so that you just know it's the difference you're dealing with. It doesn't matter for this one anyway. So this will be positive since the series is positive. So this difference is from the approximation we have. Let me copy this. We are not asked to do this one in the problem, but just for illustration's sake. Then the other one is, let me copy this one we have here. This one is this. Okay. And if you work this out, you get 0.000286651. Cool. So it means that what the bound we got here was actually correct, because this bound tells us that the exact error R10 is less or equal to this, right? So our bound was actually correct. Our bound was, this is less or equal to 0.0003 repeated, which is clearly true. Okay, so also actual error in using the average of the bounds is, let me clean this well, this minus that estimate using the bound. So this we are not sure if it's to the right or left, so we put absolute value. And this again I will copy and paste. So this one is this, and then S bar is here, copy it also. Okay, so we are doing an absolute value, this minus this, to see how well we've done in using that as estimate. And it turns out that this one is wonderful. This one turns out to be 0.000005235. Interesting. So using the average of the bounds we get from these inequalities, we see that our approximation is accurate up to 6 decimal places. But when we just use the first 10 terms, we got our approximation is accurate to maybe 3 to 4 decimal places. So there's an improvement of 2 decimal places, which is a very interesting thing to note. Okay, finally, the last problem says find a value of n so that Sn is within this number of the sum. Okay, so we know that this is true. This is true. Now, if Sn is within this of the sum, it means that this Rn is less or equal to this error, right? This Rn is less or equal to this error. So any n such that Rn, which is less or equal to here, this is this exactly, and this is strictly less than that number, 4 decimal places, will work, right? Will do. Any n such that this happens is enough. That's exactly what the problem is asking. Okay, so we don't know anything about this, but we know this, and we can use this to find n that makes this happen. So recall that this integral is 1 over 3n to the third, right? So just work this out, and then from here we get that n to the third is bigger than 1 over 3 times this is 0.00003, and n is bigger than, take cube root, 1 over 0.0003, which is roughly 32.183, right? So since n must be an integer or positive integer, any n bigger than this will work, right? Hence, you can say hence take n to be equal to 33. This is a very good starting point. Take n to be equal to 33, and that answers the problem. So what this says is that, conclusion is that if you find the first sum, 33 sum, of 1 over k to the 4th. Then the error you commit, the difference between this and the actual sum, maybe let me write it more plainly. The difference between this and the actual sum, 1 over k to the 4 minus 33. This difference is less than 0.00001, which means it's accurate to let's say 4 to 5 decimal places, and that's exactly what this tells us.